Okay, so yesterday, we ended with steam quality or the quality of steam, and we're just saying that the quality of steam is just considering the amount of vapor you have, the amount of steam you have compared to the total mass of the steam water mixture. So you're having a saturated liquid, there's some amount of vapor, there's some amount of water, but you want to determine how much in terms of mass is going to be for steam. So we also looked at the proof for this expression, and then we were able to agree on the fact that it applies to properties as well, like enthalpy, internal energy, and then entropy. Okay. And I gave this to us as an assignment to try out. So how many of us were able to do it? How many of us went through it? Okay. So for this question, we're told to consider a system consisting of a two-phase liquid vapor mixture. So we've been given the temperature that we are going to work with. And we've been given the quality of the steam as well at zero point 0.9. The question says we should calculate the specific volume of the mixture. So we already know that we are going to start with this formula. And then we know that at 100 degrees Celsius, we can read from the steam table our VF and then our VG. We're already given the steam quality, that's X. So if I put everything in the expression, I can get my value for V. Then the next question that we're also supposed to try out was saying that we have saturated steam at 100 degrees Celsius, and there's a specific enthalpy of 2000 kilojoules per kilogram. So we're supposed to now calculate the quality of the steam. So once again, we start with this expression. Then at 100 degrees Celsius, we find that HF, we find that HG. The question gave us the H. So we just make X the subject, and then that will give us the quality, right? That's what we're supposed to try out yesterday. So we'll continue with the superheated steam table. So when we say it is superheated, what we are trying to say in conditions. We have the oh, hello, hello. Okay. So when we talk about the superheated steam table, what we are just trying to say is that if I have maybe water and then it is now saturated and then part of it is becoming vapor, that is a saturation conditions. But then there's a point where I can increase the temperature further. So now it becomes a vapor. It is saturated. But now I'm increasing the temperature further, or I'm dropping the pressure further. When I do that, that steam that we have is going to become superheated because it's being heated more above its saturation conditions. So there's a point on the steam table where we can get the properties of superheated steam, right? So if we should check the steam table, let me share that screen as well. So if we should check the steam table, right? This is at saturation condition. So we can even see it up here, saturated water, right? So we know that maybe at a particular pressure, this is going to be the temperature that will make it saturated. But then what happens when the temperature is a bit higher than the saturation temperature? Then we have the superheated properties coming in. So you can even see up here that it's been labeled as superheated water. So if we check it at 0.01 megapascal, right, we are being told that at the saturation temperature, we are going to have these conditions or these properties. But then if we should increase the temperature above the saturation temperature, so maybe 50 degrees Celsius, 100 degrees Celsius, we would have other properties, or the values for the properties would be different, right? So if we should, let's say we are looking at 0.01 megapascal, we can see up here that the saturation temperature is 45, sorry, 0.81 degrees Celsius. So if I should increase the temperature further, then that steam that I'll have at that temperature and pressure is now going to be superheated because I've increased the temperature a bit further. I hope that makes sense. So that's it for the superheated steam or the superheated steam table. So that's that part of the steam table. And once again, we can read the pressure, the temperature, and then get the particular properties that we are looking for. That's the table where we have the properties of the steam, but then now the temperature might have increased above the saturation temperature. So now it is in quotes hotter than and when it was just saturated, right? So if I have maybe steam at 0.01 megapascal, you can see over here that the temperature at which it to be saturated is 45.81 degrees Celsius. So that means that at 45.81 degrees Celsius, I can have the water change into vapor. This is saturated. So if I increase the temperature further, it means I'm heating that vapor even more. So it becomes superheated. So now I'm no longer at 45.8, I'm moving up. So I've sent it to 50 degrees Celsius now. So the properties will also change. So this is the superheated steam table, the part of the steam table that deals with superheated steam. Okay. So we can an example here. So this question at 10 megapascal and then 600 degrees Celsius. So if we should go to our table, for the superheated steam, we get the pressures over here. So we are looking for 10 megapascal. So that's over here. And then the question said 600 degrees Celsius. So 600 degrees Celsius is also down here. So let me just highlight that part. So this is for 600 degrees Celsius. And we're told to find the specific volume at 10 megapascal. So specific volume is the first column. So that means that my value is going to be the 0.03837. And then our unit is meter cube per kilogram. Is that okay? Okay. So let me go back to. So that's it for 10 megapascal and 600 degrees Celsius, right? We can also, so yes, you don't. So for this one, you read the value from the table. You read the value from the table. So I'll use the next example to re-explain how we go about it, right? So now this time we're looking at the specific internal energy of water vapor at a state where P is equal to 10 bar. So 10 bar is the same as 1 megapascal. And then the temperature we're given is 215 degrees Celsius. I'll just go to the table and look for 1 megapascal now at the superheated part. So I have 1 megapascal, and then we are looking for 215 degrees Celsius. So we'll have to do what we call interpolation. So now the thing is that whenever you are giving a pressure, right, and as we said, the temperature is higher than the saturation temperature, then you work with the superheated properties. So let's say we had started out by at the saturated conditions. That would have been 1000 kPa, right? So the value would have been um, yes. So that would have been 1000 kPa. So the value would have been, what is it? 179.88 degrees Celsius, right? That would have been the value for the saturated um water if it was saturated. But now the temperature that we are working with is 215, which is higher than that 17. So if we check the saturated table first and realize that the temperature is higher than the saturation temperature, then we come to the superheated parts of the table. So now we can look for the value at 215 degrees Celsius. 215 is between 200 and then 250. So we'll work with those values to determine what we are looking for. So as I said, there's something called interpolation. Are you guys familiar with interpolation? Okay, someone says I should explain. Okay, sure. So I'll walk you through how we do interpolation as well. So the whole thing about the superheated steam table is that remember we spoke about saturated compounds or materials or substances. We said that they are at a point where they can have a phase change. So the water can become a vapor. So if I have from a table, if I have water at the 10 bar, the temperature at which it can become vapor was 179 degrees Celsius. But now the temperature that we are being given is 215. It means that we are adding more heat to what is already vapor. So we are making it superheated. So normally, if you should check from your table at 10 bar and you read the saturation temperature and you realize that the temperature that has been given to you in the question is higher than that temperature, it means that you will need the you need the heated, the superheated steam table properties before you can carry on with it. Because now you are using a temperature higher than the saturation temperature. The saturation temperature is the temperature at which it would now become a vapor. Is that okay? So what we're saying was that at 1 megapascal, we have the saturation temperature here. That's 179.88 degrees Celsius. It means that at that temperature, it will become a vapor. Oh, no, no, no. We are not saying the temperature is 100 degrees Celsius. So please remember that we said that the saturation temperature is dependent on the pressure. Is that okay? It wouldn't be 100 degrees Celsius. Is that fine? It depends on the pressure you're working with. Okay, that's good. So for this condition, at this pressure, the saturation temperature is 179.88 degrees Celsius. But we want to work with 215 degrees Celsius, which is higher than that temperature. It means that we are adding more energy or more heat. So it's going to be a superheated steam. So if you want to find a value, 215 is in between 200 and 250. So what we do is interpolation, is looking for a value in between two values that we have, right? And then the question told us that we should find the specific internal energy. So what we can do is that we can pick the internal energy at two locations and then use the temperature at the two locations as well, and then find what is in between. So this is what I'm trying to say. Let me see. Okay. So what I'm trying to say is that we are looking for the internal energy at 215 degrees Celsius, right? But then we have the values at 200. So writing is a bit difficult. And then we have the value at 250 as well. So what we want to do is that we want to find that value in between 200 and 250, which is equal to the 215. So what we do is I can say that 215 minus 200 over 250 minus 200 is equal to, so I'm picking the value of what I'm looking for. That's the 215. And then I'm using the value below it. That's the 200, right? Then divided by the value above it and then the value below it. So that's 250 minus 200 should be equal to, so 215 will correspond to our unknown. So I'll make it x minus 200 corresponds to 2622.3. So minus 2622.3 divided by 250 corresponds to 2710.4 minus 200 once again corresponded to 2622.3. So we can make x the subject, and then that will be the value at 215 degrees Celsius. It will be an approximate value at 215 degrees Celsius, right? So what we are saying is that I can look for my unknown, right, minus the value at a particular temperature. So that's going to be y minus this 2643. That was the value they read at 200 from the steam table they were using. Then we can look at the value at 250 as well. So that will come here. And then the value at 200 as well. So that will come here. Is that okay? Is that okay? Or if you like, you can consider it in this way that if the difference from the values we had on the table, 250 and 200, would be equal to 2723.8 minus 2643.3, then what's going to be the difference between the points we are actually looking for and 200? So that's also going to be an unknown minus the 2643.3. Then you can use ratio and proportion and then find your answer. And then you make y the subject. Is that fine? Okay. So we also have compressed water. When we are talking about compressed water, just the same way we spoke about superheated steam, we can have the water, maybe at a particular temperature, there's a certain saturation pressure, or at a particular pressure, there's a certain saturation temperature, right? So if we should increase the pressure further, or we should reduce the temperature, it's no longer going to be saturated. We are pushing the molecules closer together. So now it becomes compressed water. Is that okay? And the thing about the compressed water is that usually when we are compressing a liquid, you don't really see a significant change in the properties. So for some materials, you don't really get tables for their compressed components or their compressed liquid components because the properties don't really change by so much, right? But then for water, we are able to get some properties. So if we should come back to our table, we have, so this is all superheated, but we have a point where we can get compressed water. So we can see that in the heading here. So now realize that at 5 megapascal, the saturation temperature was 263. It means that at 5 megapascal, we need the temperature to be 263 before the water can even start becoming a vapor. So if I am at 20 degrees Celsius, I am way below that temperature. So it means that I'm compressing the liquid. I'm bringing the liquid molecules closer together. I'm making it cooler, right? So we can also read the properties from tables as well for some materials. Okay. So we have, so just take note of it. Just as we saw with the phase diagrams, we have superheated, we have compressed, right? And then there are tables for the different things we work with. Okay. We can come back to Oh, sorry. We can come back to um our slide. So there's also a table for other materials. Remember, we said we are dealing with water, gases, and refrigerants as the different kinds of materials or substances that we can consider for studying thermodynamics. So we are looking at a refrigerant, and there's a refrigerant called refrigerant 134A. So it also has its table. The thing about the refrigerant is that we use it for refrigeration, air conditioning, heat pumps. So there's this thing we call HVAC, that's ventilation and air conditioning. So we make use of refrigerants in these things, right? And these are some of the properties that your refrigerant has to have. Something like it's having a high heat of vaporization. You want a material that can easily become vapor, right? You want a material that has a relatively moderate density. Is that okay? And a very high critical temperature. It shouldn't be something that is corrosive or something that is toxic. So these are some of the properties of the refrigerants that we consider. Okay. And for the refrigerant table, it's also very similar to the steam table. So you also have your saturation temperature and pressure, and you can read your various properties from it, right? So some examples of refrigerants include ammonia. Okay, someone has a question. Yes, please. Please, you can ask your question.
And please,
Yeah,
my question is about the high heat of vaporization.
yeah.
Doesn't mean like you need to like put in a very high like heat before it's vapor or it's like it means like I don't know.
Doesn't that doesn't mean that you have to.
Doesn't mean that like the high heat of vaporization doesn't mean that like you need to put in so much heat before it turns to vapor or it turns to vapor at very low heat.
Okay. For the high heat of vaporization, for high heat of it means you have to. It would need enough heat before it can become a vapor. So it would need quite enough heat before it can become a vapor. So is there heat that is needed? Yeah, Francis, you can come in. Is there heat that is needed to convert the liquid to a vapor? Yeah, Francis, you can come in.
Hello. Can you hear me?
Yeah, we can hear you.
Yeah, so for the refrigerants, because their materials at a very low temperature, that means are very, very low. Something like you can take something like an ice block, like that. So they are used for cooling. They are they're at a very low temperature. So if you want to, change their phase into the vapor phase, you need a very high temperature, very high source of heat before they can be converted into the vapor phase. That's why they have a very high heat of vaporization.
Okay, is
Did
that
you get
fine?
it?
Okay. Francis, thank you. Sure. So yes, for our refrigerants, we have tables for them as well. So at particular temperatures and pressures, we can also read their various properties. And then we can do the same thing for ideal gases. So we have a table for ideal gas when we are considering air as an ideal gas. We can have a table for nitrogen, oxygen, carbon monoxide, carbon dioxide, right? So we can read their temperatures and then we can read maybe their enthalpy, their reduced pressure, their internal energy. So different properties. Okay. So we have an example here. It says that we should calculate the enthalpy change for 2 kilomoles of carbon dioxide if the temperature is increased from 25 to 100 degrees Celsius using the constant heat capacity approach. And then the next one is to use the ideal gas tables. So what we can do is that we are looking for the um, enthalpy change, the change in enthalpy. And we said yesterday that if we're looking at a change in enthalpy, we can represent it with CPDT. Is that okay? But here in the question, we were given kilomoles. So we are working on a mole basis. So what we can do is that our change in H, this is the extensive form, will be equal to the number of moles times our change in H. This is in molar form, the intensive form. So remember, this is coming from, um, remember we said that if I have H is equal to my capital H over M. And then if we have H bar is equal to my capital H over the number of moles. So if I should make this capital H the subject, I'll have N times the H bar, right? So since I'm looking for the change, it's going to be N times the change in our enthalpy in molar form. Is that okay? And we said yesterday that our change in H is equal to CPdT. And we also said that for a gas like carbon dioxide, we can represent Cp as 7 over 2 times the gas constant, right? So I can take this expression and put it in this expression. I can replace Cp here with 7 over 2 Ru and then do the integration. So if I should integrate, I'll get this expression over here. And now I know my T2, I know my T1 from the question. I know my value of Ru, and we're given a number of moles. So if I should put everything in there, I'll guess this as my final answer. Is that okay? And please always make sure your units are consistent, right? Okay. Then when we use the ideal gas tables, now the N times the change in H is just going to be N multiplying H2 minus H1. H2 is going to be the enthalpy at the final condition, and then H1 is going to be the enthalpy at the initial condition. So we are saying that we increase it from 25 degrees Celsius to 100 degrees Celsius. So you are going to read the enthalpy at 100 degrees Celsius and then the enthalpy at 25 degrees Celsius and then find the difference. So at 25 degrees Celsius or 298 Kelvin for carbon dioxide, the enthalpy was this, right? And then at 100 degrees Celsius, the enthalpy, they needed to use interpolation, like what we already spoke about, so that they can get the value. Then we just find the difference, multiply by the number of moles, and then we get our answer, right? So that was for carbon dioxide. Okay. So this is for air, this for nitrogen, this oxygen, this carbon dioxide. So we're given it was 25 degrees Celsius and then 100 degrees Celsius. So we can read 25 degrees Celsius in Kelvin is going to be about 298 Kelvin, right? So we can read the enthalpy there. So that's what we see here. And then 100 degrees Celsius is going to be about 373 Kelvin. So we realize that 373 is in between 370 and 380. So we'll have to use interpolation to get that value, right? So that's how we go about it. Okay. Then there are other places we can get thermodynamic data from as well. So remember we spoke about the fact that we can get them from certain databases and then from certain software, right? So these are other sources of thermodynamic data. So that's going to be it for lecture 2, the properties of pure substances. and then we'll start with lecture 3. But before we move on, is there any question anyone has about this part? Is there any question? No, we've not closed. We are about to start the next topic. I was finishing up what we started yesterday. You said the page before the enthalpy question. Okay, the enthalpy question. Please, can you specify, is it when we're talking about the steam quality or when we're talking about this question, the integration part? Okay, where is that one? So this is what we're seeing. I have, but are you fine with the first part? That change in H is equal to n times the change in the small h, in the molar form. Are you okay with the first part? Okay, set the page before this. Uh, so the page before it was the question. Okay. Let me unmute you so that you can ask your question directly. So please, you can ask your question directly. Okay, he said it's fine. But what we're saying about the integration was that our change in H here, we said it yesterday that it's equal to RCP times our change in T. Because our enthalpy here is in molar form, RCP is also going to be in molar form, right? And then the N that is multiplying this is a constant, so that can stay out of the integral sign. So if I'm supposed to integrate this, I'm going to integrate CP. But then CP here, we also said yesterday that we can represent it with 7 over 2 RU for some gases. So I'm going to put 7 over 2 RU in this expression. And then if I should integrate, 7 over 2 RU is a constant. So I'm just going to have this final expression at the end of the day. So it becomes N times 7 over 2 RU times the change in the temperature, the T2 minus T1. So I can just put in the values and then that would be it. But once again, please make sure your units are consistent. Because if you look at the question, we're given 2 kilomoles of carbon dioxide. That means that your R is in kilojoule per kilomole. Please take note of that. It should be in kilojoule per kilomole so that it's consistent with the value of or the units for N. If N was just in mole, then your R would be in joule per mole. So your final answer here would have been in joules, not kilojoules. Is that okay? So please pay very close attention when you are working with questions and pay very close attention to the units. Okay. So we'll take the next topic. Okay, so now we are looking at the first law of thermodynamics. When we Okay, before we get into that, so these are some of the things we want to do today. We want to define and then describe working heat. Look at the various ways that a system would exchange energy with its surroundings. Then we explain the first law. We look at it for closed and open systems, and then we look at some common devices. So when we were dealing with lecture 1, we're looking at how energy is the ability to do work. Then we spoke about the different kinds of systems we have. Then when we're looking at lecture 2, we spoke about internal energy. We spoke about kinetic and potential energy, right? So now what we want to do is that we want to look at how systems are going to exchange energy with their surroundings. And one thing to keep notes or to take note of is that energy can cross the boundary of a closed system in two ways. namely heat and work. So energy can cross a system's boundary as heat or as work. In a minute. So you can cross a boundary as heat or as work. Okay. So when we say heat, what we're talking about is the kind of energy that is transferred between two systems because of a temperature difference. Because of the fact that there's a temperature difference between the two systems. So energy is going to be transferred across them, right? So once the energy gets into a system, it is stored as internal kinetic or potential energy. So what we're trying to say is that if I have two systems in contact with each other or close to each other, one of them is at a higher temperature than the other, there's going to be some transfer of energy from one to the other. But then the way that we are going to see that the energy has been transferred is that there's going to be some kind of effects in terms of kinetic potential or internal energy. Is that okay? So if we want to make it even a bit more practical, realize that if we are using a thermometer, what is happening is that there's a temperature difference between the human body and then the thermometer. But then what the thermometer is doing is that it is taking that energy and then it is converting it into, or it is keeping it as kinetic energy. So we see the molecules now start to move. Is that okay? The molecules of the liquid in the thermometer will now start to move. So the energy, which is heat, is being transferred between two systems, but then it is going to be stored as internal kinetic or potential energy. Now, when we look at the amount of heat that is being transferred, the units or the symbol we use is Q, and the units is joules. When we are talking about rate is something per time. So now it's going to be this Q divided by time. And whenever we divide a property by time, whenever we are dealing with a rate, we have a dot on top of the symbol. So we spoke about that in CPC. And if we should consider the units, it's going to be joule per second, which is the same as watt. It's a unit of power, so it's going to be watt. Is that okay? So if we want to consider the heat transfer per unit mass, then our Q, our small Q, is going to be our big Q over M. And if we want to use maybe the heat um flow or the rate at which heat is flowing, they would need to divide it by the mass flow as well of our material so that we can get we can get the units to be consistent. So the Q up here, right, is just Q over S. And then this M here is the small m over S. Isn't that specific heat? No. We are looking at heat in general. So it doesn't just apply, well, you can consider it for specific heat, yes, but then yeah, you can call it specific heat. Okay, I guess your question now. You're saying that if we say Q divided by M, yeah, 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 you can call that specific heat, yes. One thing to notice, you see, if you're talking about extensive and intensive, usually we are dealing with properties. So we are not looking at heat as a property. The properties are things like pressure, temperature, specific volume, maybe the kind of kinetic energy it has, its internal energy, those things, right? That's why I was really explaining the issue about heat being that which is transferred, but then how it is stored is as maybe internal energy or kinetic energy. So those ones are the properties we consider, right? So if we are talking about it as a property, we don't consider things like heat and work as properties of a system. But then if we want to determine the heat for a given mass of a material, we can divide it by M. Is that okay? Okay. But remember, we also said if we are looking at energy, um, energy would be extensive in nature. Do you get it? So if we should divide by the mass, we can make it um more intensive and we can make it specific, right? So you can consider heat in that sense of energy, but then we are not considering heat as a property. So please just take note of that. Okay. So when we have a process where there is no heat being transferred, then we can call that an adiabatic process. Usually this happens when we have a perfect insulation or the two bodies in contact at the same temperature. You can call it specific heat. Yes, it's fine. So heat that's gained by a system will be denoted as positive, while heat that is being lost by a system is going to be taken as negative. So please keep this convention in mind. Heat that is being gained by the system, if the system is gaining heat, then it is positive. But if the system is losing heat, then it's going to be negative. Okay. Yes, another thing about the um, adiabatic process, when we have the temperature of the system and then the surrounding also being the same temperature, realize that there wouldn't be heat transfer between the system and then the surrounding. So that is also going to be an adiabatic situation. Is that okay? So maybe our system is perfectly insulated so that there is no heat transfer between the system and the surrounding, or the system and the surrounding are at the same temperature. So when they are at the same temperature, heat won't be transferred between them. Okay. So now we can consider work. When we talk about work, work is a force that moves through a distance. So we can have parts of our system or certain units in our system that would be moving, right? Pushing some amounts of force across a distance. So we can have a piston, we can have a shaft, can even have an electric wire. All these things are going to bring out some form of work, right? Because they will have certain interaction. They are going to cause some force to move through a certain distance. And the amount of work that's going to be done between one state and the other, we are going to denote it with the letter W. The unit is also going to be in joules. Then if we consider the rate of doing work, is going to be RW divided by time. That's RW divided by time. So we'll have the unit to be in joule per second, right? And just as we saw with the heat, we can have it as just the work done for a given mass, or we can have the rate at which work is being done divided by the mass flow rate. But for this convention, when we see work that is done by the system, then it is negative. When work is done on the system, then it is positive. Is that okay? Okay. So the similarities between the two of them are we recognize both of them at the boundaries of a system as they cross their boundaries. So they are called boundary phenomena. They are called boundary phenomena, right? So that's what I was really trying to speak about earlier. The fact that for heat and for work, we recognize them as they are being transferred, maybe across the boundary. But then we don't take them directly as a property of the system, right? So our systems can possess energy, but then they don't possess heat or work. Is that fine? So they can have internal energy, they can have kinetic energy, they can have all these kinds of energy. But then we don't say that the system has heat or the system has work, right? And then both of them are related to a process, not a state. Remember, we said for a state, we define a state by certain properties that the system has. So maybe the system is at 25 degrees Celsius and 1 bar. We can define that as a state of the system. But we can say that the system is at 25 degrees Celsius and then at a work of 20 joules. So we don't use heat and work to define the states, but then they're related to the process. So we can say that in moving from maybe 25 degrees Celsius and 1 bar to 30 degrees Celsius and 1 bar, I needed to add this amount of heat to it. Is that okay? So now that one is related to the process. It's related to the change in the state. So we can relate heat and work to the process. That's which is going to cause the state to change. But then they are not used to define the state itself. Okay. And they are both path functions. So their size will depend on the path that you are going to take. So for example, somebody wants to heat water from 25 degrees Celsius and then end at 100 degrees Celsius. But then the person first starts at 25 and then overheats it to maybe 150 and then now comes back to cool it and it drops to maybe 90 and then he heats it again to 100. Another person heats it from 25 directly to 100. Realize that one person has put in more energy compared to the other. The size of the amount of heat, right, depends on the path that they follow. And it also depends on the final stage that they end at as well. I hope that makes sense. So their path functions, it depends on the path we follow. Remember we said the path are all the intermediate states that we would follow when we are moving from our initial state to our final state. Okay. So we can have different forms. Okay, someone says I should come again with that point. So what we're saying about the path function is that we can have a case where we are I want to give a little example with this. Okay, so let's say that we have somebody who is supposed to walk from the ground floor to maybe the second floor. Yes, the second floor of maybe PB, right? One person can decide to just go straight up the stairs. Another person might go all the way to the fourth floor, come down to the second floor. Realize that they are both ending at the same state. They started from the same state, they ended at the same state. You get it? So now they are both on the second floor. If you should look at their states, they are both on the second floor. But one person did more work than the other. So it depends on the path that you take to get to the state you are looking at. Does it make sense? So we can all end at the same state, but the path you use or the process you use is going to determine whether you use more heat or more work compared to another person. Sometimes one system might use more heat and less work, and then you get at a point. Another system might use um less heat, more work, and then get at the same point. Is that okay? So it depends on the particular pathway you use to get to your final state. Okay. So the different forms of work, we can have mechanical or non-mechanical work. So non-mechanical work is work like electrical work, which we are not going to really be interested in thermodynamics. But when we look at mechanical work, we're looking at a force that's going to move some form of resistance across a distance. So things like shaft work and then flow work. So shaft work, we are looking at the moving parts of our systems or of our devices. So we can have a piston or a rotating shaft. All these things are going to be shaft work. And then we have flow work. That one is based on the movement of material in and out of our system. So the work that those materials are going to be introducing just because they are moving in and out of our system. Is that okay? Okay. So for the mechanical work, when we look at work that is done on thermodynamic systems, we have shaft work and then we have moving boundary work or boundary work. So the work expression or the work term, you can express it in this form. The WS here is representing our shaft work. And then this term here, the integral of PdV, is representing our boundary work. So this is considering the fact that there's going to be movement of our boundary, right? So the volume of our material will be changing. So if you look at the animation we have over here, you realize that as the process is going on, we see that it compresses and then it expands at some point. So the volume of whatever is in there keeps changing. So there's some amount of work that is being done. But then these rotating parts are also coming with some form of work. So the parts that are rotating are going to introduce the shaft work. And then the part that is doing the compression and the expansion, where we see the volume changing at the boundary, is going to be the boundary work. Is that okay? So we see here that the expansion and compression of a fixed mass of gas in a cylinder movable piston arrangement, we can use it to explain the moving boundary work. And that's a primary form of work that's involved in automobile engines and reciprocating compressors. Is that okay? So that's it for boundary work and then for shaft work. And then when we put the two of them together, we get the work expression. Someone says they're not fine with this. So what we are trying to say over here is that, remember we spoke about the fact that we are looking at heat and then we are looking at work. But when we look at the work term, we can break it into two, um, let me say, subunits. So we have parts of the work coming from what we call shaft work. This is coming from things like our rotating parts in our system. And then we have boundary work, which is what we see with the first expression here. That's the integral of minus PdV, right? So what we are saying by this is that there's a certain change in the volume of the material we are working with. And this is going to constitute what we call boundary work, because now the volume is changing because the boundary is also moving. Is that okay? So if we look at this part here, the animation, realize that as the system is moving up and down, you see that the volume of the material in the cylinder would reduce and then would increase as we are compressing and then as we are expanding it, right? And as that boundary moves. So that's what constitutes what we call the boundary work. Is that which is going to cause a change in the volume. Is that okay? So the reason why it's negative, remember our convention, we're saying that we would need work to be, or with our system, when work is being done, then we are saying that it's going to be negative. When work is being, so when work is being done by the system, it's going to be negative. When work is being done on the system, it's going to be positive. So if we were using the other conversion, then we would have kept that one as positive, right? So this is just so that when we get to the first, when we write the expression, what we are going to get is going to be consistent. Someone is asking that which one is the shaft. So um okay, there's a shaft, but then there's also shaft work, right? So the shaft can be this portion here. Is that fine? But then the shaft work is considering even parts that are rotating. Is that okay? So we can have this middle piece here that is rotating. It's introducing some form of shaft work. Is that fine? Okay. Okay. So when we consider boundary work, we're seeing that we are looking at the expansion of a gas from a volume V1 to V2. And the work that is going to be done is going to be the area under the curve. Remember, we said we're looking at an integral of P dV. So if I have a PV graph, a pressure volume graph, and I plot my process path, the area under that is going to give me the work that is being done, right? And we are seeing here that the amount of work that is done is dependent on the path. So remember we said that work is a path function. It depends on the path you take. So if we look at this over here, the graphs we have over here, what we are saying is that the area under this curve will give us an indication of how much work was done in moving from point one to point two. But someone might use a different path. So maybe I'm moving from point one to point two. Someone uses path A. If we should find the area under that curve, realize that it's going to be a larger value. The magnitude is larger than if we should find the area under B. And that will also be larger than if we should find the area under C. So they are all different pathways moving from the first state to the final state, causing an expansion. So we are increasing the volume. But realize that the area under each of them are different. So work is a path function. It depends on the path you take. It's not a state function. It doesn't depend on the initial and the final state. Is that okay? Please, are we fine with this? Okay. So now we have what we call polytropic processes. And when we are doing expansion and compression of gases, we can write this expression. So this is an expression for what we call a polytropic process. A polytropic process is just a process that obeys this relation. So we have our pressure and then our volume, and then a certain constant. It should be equal to C. So C is going to be a constant, right? Okay. So in the case where N was 1 and we're dealing with an ideal gas, we could have said that PV is equal to RT. So our C here becomes RT, means we are keeping our temperature constant, right? So remember, we also said that work is equal to minus PdV. If we are not considering shaft work, we are just going to consider the boundary work. So it's minus PdV. And we are going to integrate it from V1 to V2. So what we can say is that we can make P the subject from this relation. We can make P the subject from this relation here. So that's going to give me C divided by V over N, right? So let me see if I can write a bit. That's C divided by Vn, or C V to the power minus N. So that's what we see over here. Now I can replace, the pointer isn't showing. Okay. So I can replace the P, which we've said is C times V to the power minus N. I can replace it with this P here. So that I'll have C V to the power minus N dV. Then the rest of it is just algebra. The rest of it is just algebra. So we are going to do our integration. And then if we do our integration and put in the limits, we should end up with this expression, right? So it's something that I'll let us try out, and then I'll write it out and also send it to you. But then this part is just math. So it's just calculus and integration. So if we should integrate this and put in the limits, we'll get this expression here. We can multiply through by C. But remember we said that PV to the power N is equal to C. So it means that for every pressure and volume at a particular state, it's always going to give me a constant value. So if I have the pressure and the volume at state 1, and I have the pressure and the volume at state 2, they are always going to give me a constant value. That's what the expression means by P to the power N is equal to C. So the C we have here, right, when we multiplied it, we had CV to 1 minus N minus CV1 1 minus N. We can replace the C here with P2 times V2 or P1 times V1. So what I'm saying is that this C we have here and this C we have here, we can replace them with P1 V1 to the power N and then P2 V2 to the power N. So when we do that, we realize that we end up with this expression here, the expression we have here for W. And we can simplify it further. So this V2 to the power 1 minus N, it can become V2 times V to the power minus N. And then that V to the power minus N can cancel out this V2 to the power N. So yes, this is V2, right? And when we do that and simplify, we are going to end up with this expression over here. Is that okay? So it's just math from this point. What we are saying is that W is equal to minus PdV, and we are integrating from V1 to V2. But then we also know that PV to the power N is equal to C. So we are just going to make P the subject, put that in this expression, do our integration. And the other point you need to take note of is that PV to the power N, we said, was equal to C. That means that for every pressure and volume at a given state, it's going to give me a constant value. So the pressure and volume at state 1 and the pressure and volume at state 2, if I should put them in the expression, they will give me the same constant value. So I can equate them to each other. Then everywhere I see C, I can replace them with P1 V1 to the power N or P2 V2 to the power N. So when I do that and simplify, I'll end up with this expression over here. Now, if it's an ideal gas, then we can express the P, the pressure, or the PV, right, as MRT. So if we do that, we can factorize the MR out, and then we end up with this last expression down here. So I would ask us to prove this. You can send me your solutions by the close of the day. And then if you get stuck, I'll just um, assist you with that. But I hope you get the idea behind what we are doing over here. We are just making P the subject in this expression. We put it into our expression for work. We do our integration, we do our substitutions, and then we simplify. Right, so I want us to try that out. Okay. Now, in the case where all of these happen when n is not equal to 1, right? So in the case where n is equal to 0, what it means is that p v to the power n is equal to c. N is equal to 0. Anything to the power 0 becomes 1. So in effect, we are just saying that p is equal to c. So in that case, what we are having is an isobaric process because now pressure is constant. That's what we are trying to say. So that's what we are trying to say from this first point here, that when n is equal to 0, p will be equal to c. So p1 will be equal to p2. So I can put that in this expression here and then factorize p1 out. And I'll get this expression now. Is that okay? In the case where n is equal to 1, you realize that we'll be having c times v to the power minus 1 or c over v, right? So what is going to happen is that I'm going to be integrating c over v. And when we do that, that's where the natural log comes in. So if we should integrate this, we would have c ln v from v1 to v2. Then I can put the limits in there. So when I do that, I'll end up with this expression we see over here. Is that okay? And once again, we said that c is going to be equal to pv to the power n. Our n is 1. So c is just going to be equal to pv. And that means it's going to be equal to nRUT or MRT. So I can replace the c over here with any of these terms, and then I'll get my final expression. Is that okay? What we see happening in the brackets is we have our volumes. We can divide them by mass and then get the specific volumes. Is that fine? Okay. So that's it for this part. A second. Okay. Yes, so realize that when our n is 1, right, we are going to have an isothermal process because nRUT is going to be 1. And then when our n is going to be infinity, then what we are going to have is going to be a constant volume process, so an isochoric um yes, an isometric process. So if n is infinity, then it means that v is going to be a very large value. So it's going to be so large that p can be neglected. So then our v term becomes the constant. So it's going to be a constant volume process. So it's just one thing that you can keep in mind. Okay. So now we can go to the first law of thermodynamics. It's also known as the law of conservation of energy. So I know that this is something we are familiar with. So what does that law state? I want someone to answer. What's the first law of thermodynamics? Or what does the law of conservation state? Anyone? Okay, thank you, Obed. So We don't create, so we don't destroy energy, but we can change the form of energy we are working with. Another way we can state the law is that for all adiabatic processes between two specified states of a closed system, the network that is done is going to be the same, regardless of the nature of the closed system and then the details of the process, right? So it's just another way of seeing the same thing. Thank you, Amanda. Right. So we are saying that if it's an adiabatic process, there's not going to be any transfer of heat between the system and the surrounding, or there's not going to be any form of transfer of heat, right? And then we are having two different states. So it means that the system is moving from one state to another state in a closed system. Then it means that the amount of work that is going to be done at the end of the day is going to be the same, irrespective of the process that occurs. If it's not the same, then it means that there was some kind of energy that was coming from somewhere else. Okay. So if a system has experienced an increase in its total energy, then it means that the energy has been transformed or transferred into the system across the boundary. But if the energy in the system should decrease, then that energy is also being lost across the boundary. Right. So let's keep that in mind. So the first law, we can say that the change in the amount of energy that the system is having, right, is equal to the net amount of energy that is going to be transferred by heat, then minus the net amount of energy that will be transferred by work. And then that same change in the energy within the system. Remember, we said this yesterday that we can consider it as a potential energy, kinetic energy, and then internal energy. Right. So what we are trying to say is that if I should, or since these two are equal, then it means that everything to the right hand side will be equal. So the first part here is our Q. This expression down here just means that the change in energy within the system, that's the final minus the initial energy of the system, is going to be equal to our Q plus W. And then this change in energy in the system, we are also seeing it by this second point here that we can equate it to the change in the potential energy. That's the change in PE here, the change in kinetic energy, and then the change in internal energy as well. So at the end of the day, our expression for the first law is change in U, this for closed systems, is change in U plus change in PE plus change in KE to be equal to Q plus W. Then we can also decide that we want it in the derivative form. We want to look at the change on a very small level. So we can just differentiate each term, right? And we can decide that we want this on a rate basis as well. So we can differentiate all of them with respect to time. If we should do that, we would end up getting the left-hand side this way. And then here we would have our heat as a heat flow. And then we can also have work. No, we won't have work flow because it's a closed system, right? So if it was an open system, then we can have work coming in. Well, we can have the rates at which work is done here. So we can still have our plus W with a dot on top. Then another way we can also write it is this term here is relating to the potential energy. So you know that potential energy is mass times acceleration due to gravity times height, right? And then this here is related to the kinetic energy. So we know that kinetic energy is half times mv squared. So what we are doing is that we are dividing everything through by mass. That's why we are not seeing the mass term in there, right? And then our u here is just going to be the change in. So the u final minus u initial. Is that okay? So this is representing the change in the internal energy. This is representing the change in the potential energy. This is representing the change in the kinetic energy. And this representing our heat and then our work. All of them are divided by mass for this expression. Okay. So we have an example over here. The question tells us that a rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kilojoules. So during the cooling process, the fluid is going to lose 500 kilojoules of heat, and the paddle wheel will do 100 kilojoules of work on the fluid. So you are being told to determine the final internal energy of the fluid. We should neglect the energy that is stored in the paddle wheel. So we take our terms one by one. But what we normally do is that we have to start from our equation, right? So we are told that it's a rigid tank that's containing a hot fluid and is being cooled. We are not seeing any movement of material into and out of the system. So we know that we are working with a closed system. So we can start with our relation where we have our change in U plus our change in KE plus our change in potential energy to be equal to our Q plus our W. And we can see that there's no kinetic energy being spoken about in the question, or nothing that indicates kinetic energy. Can also assume that potential energy is going to zero. So kinetic and potential energy are going to zero. So at the end of the day, we are going to just have our change in U to be Q plus W, right? So our change in U can be our U final minus our U initial to be equal to our Q plus our W. Now, as we look at this, the question gave us very important things to take note of. So if you look at the question, it says a rigid tank. When we say a rigid tank, what are we talking about? If we say the tank is a rigid tank, what are we talking about? So I think we came across this in physical chemistry as well. So when we say a tank is a rigid tank, what are we talking about? Any answer? Any answer? Okay, so when we say the tank is a rigid tank, what we are saying is that the volume is not going to change. The volume of the tank is not going to change. But remember that we said if we want to consider work, we said that our W is equal to minus integral of P dV plus our shaft work. If the volume isn't changing, it means that the V is zero. There's no change in volume. So this whole part of the expression can go away. So all that we are going to be focusing on is going to be the shaft work, right? And the shaft work was given to us in the question. Because the question said that the paddle wheel does 100 kilojoules of work on the fluid. So that's the shaft work that we are going to have. Is that okay? Okay. So we have our expression RUF minus RUI is equal to RQ plus RW. Now the question told us that the initial internal energy was 800 kilojoules. So we have that value. So that's that the fluid loses 500 kilojoules of heat. So that is heat lost. So that's going to be negative. And then the paddle wheel does 100 kilojoules of work. So if the wheel is doing the work on the system, then that value is going to be positive. Is that okay? So as we can see, we started with the first law. We cancel out potential and kinetic energy, right? And then for our work term, we express it in this form. But then we have a rigid body, so dV is zero. So it means that this whole part of the expression can go to zero. This whole part of the expression can go to zero. And we are just left with the shaft work. Then we are saying that for our system, usually we are considering that there is no potential and kinetic energy change. So our change in U is just going to be our Q plus our shaft work. And we said the change in U was going to be U final minus U initial. Then once again, we said our Q, the heat was being lost, so it's negative. That's minus 500 kilojoules. For the shaft work, the work was being done on the system by the piston, so that's 100 kilojoules. And then the initial internal energy we had was 800 kilojoules. So if we should put all of that into the expression, the UF minus UI is equal to Q plus WS, and we make UF the subject, we'll get our UF to be 400 kilojoules. Are we okay with this? Okay. Now we can also have an open system. So in this situation, we are going to have material flowing in and out of our system. So now this is where we have flow work coming in there, right? Because now we are having work introduced into the system by virtue of flowing materials moving in and out of the system. And we did this in CPC, where we said that the flow of mass out or the mass flow out should be equal to our mass flow in plus our accumulation. or basically our accumulation should be equal to the flow in minus the flow out. Is that okay? You're not dealing with reactive system, so you're not considering generation and consumption. So we have flow out minus flow in to be equal to accumulation. Now, this is how we usually write it. So for accumulation, it is just d. Let me not use m for now. So let's say it's x dt. X representing any um, property or variable. So in this case, it is mass. You can have a case where it is energy. So if I have the derivative of something with respect to time in the system, that is representing the accumulation term. All we are saying by that is how much of the material are we going to get in the system as time moves on? That's the accumulation term. Or how much change in the material or in the property are we going to have in the system as time moves on? So that's the accumulation term. And what we said was that it is equal to the flow out minus the flow in. So if we should um okay, yes. If we look at this, we can have this first expression here and then this second expression here. This first expression here is considering all the flow coming in. And then this one is considering all the flow coming out. Is that okay? So you're looking at all maybe or the system you have might have more than one inlet, more than one outlet. You have to consider the flow in all the inlets and then the flow in all the outlets. Is that fine? So for a single inlet and a single outlet system where we have just one inlet and one outlet, then we have our accumulation to be equal to our in minus our out. Is that okay? But when we are at steady state, remember we said at steady state, there is no accumulation. So the MDT can go to zero. So our in is equal to our out. Is that fine? Please, are we following? Okay. So what we are saying by this is that we first looked at closed systems where there was no flow of material in and out of the system. But now we have a case where we are dealing with an open system. So for open systems, we said material can flow in and out of the system. And when we're looking at CPC, we spoke about the fact that we can have the flow in minus the flow out plus generation minus consumption to be equal to accumulation. But we said we are not dealing with a reactive system. There's no reaction happening. So we are not going to consider generation and consumption. So we just have flow in minus flow out to be equal to accumulation. What I was saying was that the DMDT here is representing the accumulation term, right? The accumulation of mass in the system with respect to time. So how much the mass of the system is going to change will determine how much mass has accumulated in the system with time. And then this first term here is representing all the inlet streams we can have. And this is representing all the outlets we can have. Because remember we said the accumulation is equal to the flow in minus the flow out. So if I have a system that has three inlet streams, I have to consider the flow in for all those three streams. If the system has two outlet streams, I have to consider the flow out for all those streams. That's why we have the summation here. So it is adding the flow of all the inlet streams. This is adding the flow of all the outlet streams. But in the case where we have just one inlet and just one outlet, then our accumulation is equal to just the mass flow of that inlet stream minus the the mass flow of the outlet stream. Are we okay with that so far? Please, are we okay with that so far? Okay. Then we also said that when we are at steady state, there is no accumulation, right? So the MDT goes to zero. So if the MDT in this expression goes to zero, then it means my M in should be equal to my M out. Is that fine? So the mass flow coming in will be equal to the mass flow coming out. Is that okay? Okay, that's good. So we can do the same thing considering energy. So for energy, our change in energy with respect to time, that's the accumulation of energy, will be equal to the energy that is flowing in minus the energy that is flowing out, right? And then when it is at steady state, then the in becomes equal to the out because accumulation will go to zero, just like what we saw for the mass. So the in is equal to the out. But I realize that there's a dot on the top. So you're dealing with the rate of energy, the rate at which energy is flowing. So it is something per time. Now for the energy coming in, it is going to come in with its own heat, its own work. And these terms here, I'll start with the last one, the ZG. This is going to be the potential energy because the potential energy is mass times acceleration due to gravity times height. We don't represent height with H for thermodynamics because H is for enthalpy. So we use Z, right? So mgz. Then the next term here is for kinetic energy. So mv squared over 2 or 1 over 2 mv squared. And then the first term here is for enthalpy. So the energy coming in or the material coming in is coming with its own heat, its own work or shaft work. It's coming with its own enthalpy, kinetic energy, and then potential energy. And when this is going out, it is going out with some kind of heat, some kind of work, some kind of enthalpy, kinetic energy, and then potential energy. So now we can group the terms. So I can take everything that is heat to one side, everything that is work to one side, and I can send all the enthalpy and kinetic energy and potential energy to the other side as well. So when I do that, I'll end up with this expression here, the last but one expression here. Then I can simplify it even further. So if I should simplify, what I'm going to get is my Q plus my WS coming back in, right? And then I have the sum of all my, maybe I have more than one stream. So I have the sum of all the outlet streams with their enthalpy, their kinetic, and then their potential energy, minus the sum of all the inlet streams with their enthalpy, their kinetic, and then their potential energy. Is that okay? Please, is that okay? Okay. So if it's just one stream, then the summation term doesn't have to come in there. If someone says no. And he's the one who says no. Is there, let me know the part you want me to go over. So you can unmute and then tell us. Or you can just type it out. The part you want us to go over. Please, I'm waiting for you. Okay, then let's go on. So when we have a problem and we want to solve it, what we need to do is that, oh, sorry. When we have a problem that we are solving, there are some steps that we can follow. So we will be given a question, and you should be able to rephrase the problem in a manner that is simpler, something that is concise. You might have a very long question with so many um, different things being said, but you should be able to fish out the necessary information. So remember when we're doing CPC, there was a question that came up, and then Doc was mentioning the fact that there were some parts of the question that were just there to give you information, but you wouldn't use it to solve the question. You should be able to read the question, pick out the relevant information, and know what you are working with. One other thing that would also really help you is if you are able to have a representation, maybe a diagrammatic representation of what you are doing. So you can draw a sketch of the problem. Then you can look at all the assumptions and then the approximations that you can make. So there are some assumptions that you can make that will make it easier to solve the question. But your assumptions and your approximations should be reasonable. It should be reasonable based on the kind of question you have. So we'll see examples of that as we move on. Then we can also consider the physical laws that are there. So there are some laws and some principles that you can use that would make solving your question easy. And then you also need to know the properties of your material at the state that you are working with. So maybe your question tells you that you have water at condition A and then at condition B. You should be able to use either your equations or your tables to be able to determine the properties that you use it to solve the question. Maybe your question is saying that you need to do something and you need to find enthalpy. So you find the enthalpy as condition A, you find the enthalpy as condition B, and use it to solve the question. Okay. A minute. Sure. So we can continue. Then we can now do our calculations. And when we are done, we check to make sure that the results we've gotten are reasonable. Okay. So we look at different kinds of equipment that we can use or that we work with. When we are looking at the energy balance of systems, we can consider things like turbines, compressors, pumps, throttling valves, heat exchangers, nozzles, and diffusers. Right. So we'll be taking them one by one. When we talk about a diffuser, this is going to be a device that can increase the pressure of a fluid by slowing it down. A nozzle does the reverse. So the nozzle rather increases the velocity and then rather reduces the pressure. Is that okay? Okay, so these equipment, they're just used to convert mechanical energy to fluid pressure or to produce mechanical energy from high pressure fluid. So we'd see how that works. So you use these things usually with jet engines, rockets, spacecraft, and even garden hoses. So that if you have a garden hose, for example, right, and the water is flowing out of it, it's moving at a certain pressure and at a certain velocity. But then if you should cause a constriction, like if you should block a particular part, right, then it's now going to act like a nozzle. So you're going to have a case where the velocity is going to increase, but then the pressure will drop. Is that okay? Okay. So when we are dealing with nozzles and diffusers, usually this is how we symbolize nozzles. This is how we symbolize diffusers. So for nozzles, what's going to happen is that we are going to cause it to become more constricted, or there's a part that is more constricted. So it's going to resist the fluid flow, right? And when that happens, the pressure is going to drop and then the velocity would increase. So it comes out like a jet because you're increasing the velocity. But then when you have a diffuser, it's rather the reverse, right? So you are dropping the velocity instead, and then the pressure would rather increase, right? So remember we had this expression. This was our energy balance relation. When we're dealing with nozzles and diffusers, we are working with the assumption that there is no heat that is being transferred. So Q is zero. There is no shaft work. So W is zero. The WS is zero. We're also assuming that we are at a constant elevation. There is no change in the height. So our change in Z is also going to be zero. So when we have that, it means Q is zero, W is zero. The Z here and then the Z here are going to cancel out to give zero. So this and this go away. So what we are left with now is just going to be the change in the enthalpy and then the change in the kinetic energy. So for nozzles and diffusers, when we simplify, we are going to end up with this expression. Right. So remember we said over here that we work with reasonable assumptions. That's what we are trying to talk about here. So for nozzles and diffusers, it's reasonable to assume that there's no heat transfer. Even if there is any heat that's going to be generated, it's so small, it's negligible. There is no shaft work because you don't have any shafts or rotating parts or any moving mechanical parts that would introduce some form of shaft work. And then we can also reasonably assume that we are at the same elevation. There's no change in height, so there's no change in potential energy. So we can cancel out all those terms. And then the only things that to be left with are going to be our change in our enthalpy and our change in our kinetic energy. So we can decide to make our change in enthalpy out the subject. And then we end with this expression. So one thing to note, for nozzles, the enthalpy out is going to be less than the enthalpy in. Remember we said that for nozzles, the velocity of what is coming out is higher than what is coming in. So let me, okay. The velocity of what is coming out is higher than what is coming in. So if the velocity coming out is higher than what is coming in, it means V2 or V out squared is greater than V in squared. So the overall expression here becomes negative. So H out is going to be H in minus something. That's why it's less than H in. And then for diffusers, we said that the velocity is going to increase when it's coming out. So we said it's going to decrease. So it means the V out is going to be smaller than the V in. So this whole expression here remains positive. So H out is going to be H in plus something. Since it is plus something, the enthalpy out is going to be greater than the enthalpy in. So if you are solving a question and you are dealing with maybe a nozzle, you are dealing with a diffuser, I mean, this can help you have a fair idea of what to expect. Should my enthalpy be greater than or less than what was coming in? Depending on how the question is framed. Is that okay? Okay. Then we can also have a turbine. So a turbine is a rotary mechanical device. It just means that it has a rotating part and is able to take energy from a flowing fluid and then convert it into useful work. Right. So this work that is produced, we can use it to generate electrical power. So we have an idea of how simple turbines work. We have a device. There's a fluid that flows over the blades of the device. It causes some kind of rotation, and then we can generate energy from that. Right. Some of the fluids that we use to transfer energy, we have steam, we have some gases, we can even use air and then water. Right. So the two turbines that we are really interested in are the steam turbine and then the gas turbine. Okay. For the turbines, you can have different kinds of turbines based on their mode of operation. So we can have an impulse or a reaction turbine, a condensing or a non-condensing turbine, and then we have pressure level turbines. So this is how the impulse turbine looks like. So we just see that it's going to shoot a jet of air fluid. It could be steam, could be water, and it's just going to cause the blades to rotate, right? So what happens is that we are um yes, we'll have steam that will pass through a nozzle. So it's going to come out at a higher velocity. So when it comes at a higher velocity, because it has a very high speed, it's going to hit the turbine and then will cause it to rotate. Is that okay? So this is what we call an impulse turbine. Then we have what we also call reaction turbines. So for reaction turbines, they have not just moving blades, but then they also have fixed blades as well. So some of the blades here are not going to be moving, and it alternates between moving and then stationary, moving and stationary. So as your fluid is passing through the blades, the fluid now begins to expand. And then as it expands, the pressure will drop at some points, and then it will cause you to now generate your energy. And these are the graphs for the change in the velocity and pressure when you are dealing with impulse and reaction turbines. So for the impulse turbine, the velocity of your fluid would first increase because remember, we said we are using a nozzle to shoot out maybe the steam or the water. So the velocity increases, but then the pressure would now be dropping. Right? I think we already spoke about that. So the pressure would now be dropping. And it gets to a point where the velocity would now decrease. But at that point, the pressure is just going to be constant. Then we can also have a reaction turbine. So for the reaction turbine, the velocity would increase, but then the pressure would just be dropping steadily across the system. Then the velocity would now decrease again, but then the pressure will still be dropping steadily. Right. So I'll send the material to you so that you can see the animation. And I'll send you other things as well so that you can use. We also have condensing steam turbines. So for these ones, what happens is that we have steam coming out with maybe a very large amount of heat, and then we allow it to cool over the turbine we are working with. So now we are going to work based on the amount of heat that we are using from the steam. Doesn't mean that all the turbines use nozzles. Yes, there's some form of nozzle at a point, especially with the impulse and the reaction turbines. There's a nozzle at a point. So there's a nozzle to shoot the fluid here, and there's a nozzle here too for these ones. But then, okay, well, yeah. Then for the non-condensing steam turbine, unlike the condensing steam turbine, where we are looking at the heat, so we are looking at the steam coming out with a lot of heat, and we are going to pass it through the turbine with the aim of getting it to condense. So it's going to lose energy to the turbine. In this case, we are not looking so much at the heat. We are looking at the amount of work we can get from the steam. So for these ones, we use the steam at very high pressure, and then it will come out at atmospheric pressure, right? So that change in pressure is going to be translated into some form of rotation and some form of work. Okay. And we also have compressors. So compressors are just mechanical devices that you can use to increase the pressure of a gas by reducing its volume, right? So we have pumps and we have compressors. So compressors are for gases, pumps are for liquids. Is that okay? And there are different kinds of compressors. So there are two classifications. We have positive displacement, then we have the dynamic, and then we have examples of them. This is an example of a positive displacement pump. So we can see that it is going to um, increase the flow of the fluid by this movement that we can see here. The sense looks similar. Okay. So these are examples of the compressors we can have. So we can have a double acting reciprocating compressor, or we can have a single acting reciprocating compressor. So for the double acting, what we can see is that as it moves in one direction, fluid is drawn in at one point and then it is pushed out at one point. And as it moves in the other direction, fluid is pushed out from the initial point where it was being drawn in. And then the point where it was, well, let me put it this way. Realize at this point here, when it becomes blue, it means fluid is coming in. When it becomes red, it means fluid is going out. So we can see that both of them are happening at the same time. But unlike in this situation where when it comes down, that's the only point where fluid comes in. And when it goes up, that's the only point where fluid goes out. And we can also have the lobe type rotary compressor. So we have these two lobes within the compressor. And as they rotate on each other, they are able to draw fluid in and then push fluid out. So they create some points that have vacuums, and then they create some points that have enough pressure to push the fluid out. And it's a similar thing with the screw type, but then this time instead of it being in this shape, it's in the shape of a screw. We also have centrifugal or radial compressors. So these ones work based on centrifugal action. So as the fluid moves into the compressor, by centrifugal action, as we can see here, it's going to move it to the end of the blade and then push it out. Then we can have those that are moving along the axis. So instead of it moving to the ends, that's based on centrifugal action. This time it's moving along the axis of our compressor. Okay. So for turbines and for compressors, once again, we'll have to start with the general energy balance equation. And we can assume that the amount of heat change that we'll see is going to be very small, very negligible. So it's approximately zero. We're also going to assume that there's not a significant change in elevation. So that one is also going to be approximately zero. And we can also assume that the change in the kinetic energy as well is also going to be very small. So at the end of the day, all that we are going to be left with will be our enthalpy change and then our shaft work. We can't neglect shaft work in this case because we are dealing with rotating and moving parts that are introducing some form of work. And one thing to note is that for turbines, our shaft work will be negative. For compressors and for pumps, our shaft work is going to be positive. Is that okay? Is that okay? Okay. So we have an example. Oh, someone is asking why is it so? Okay. So remember we said that when we are dealing with work, right? Work that is going to be done on the system is was it negative? Please let me confirm. Sometimes the convention confuses me too. Yes, we said work done by a system is negative and work done on the system is going to be positive. Okay. Okay. So if work is being done on the system, we are seeing that that is positive. Compressors and pumps are doing work on the system. So they are compressing the fluid. They are acting on the fluid. But for turbines, It's more of the fluid doing work on the system. So if we have a turbine, maybe we have the gas expanding, and then the gas is what is rather um, causing a rotation somewhere. So that's one is negative because now the system is what is rather doing the work. But for the compressors and pumps, we are rather doing the work onto the fluid we are working with. Is that okay? Okay, sure. So we have an example here. We say that steam enters a turbine at 4,000 kilopascal and 500 degrees Celsius, and it leaves as shown in the figure. So for an inlet velocity of 200 meters per second, calculate the turbine power output. You are being told to neglect any heat transfer and kinetic energy. Ensure that the kinetic energy change is negligible. Right. So for the first situation, we are still going to start out with this expression. And then we are being told that we should neglect any heat transfer and kinetic energy. So our Q here goes to zero, our kinetic energy goes to zero. So the V squared over 2 terms cannot go away. We are assuming that there's no change in the elevation. So our potential energy can also go to zero. So what we are going to end up with is this expression here. Our Ws is equal to our mH2 minus H1. Right. So we started with a general energy balance. We cancelled out the terms that we were not focusing on. And then we ended up with Ws equal to our mH2 minus H1. Now, H2 is going to be the enthalpy at the outlet, and H1 is the enthalpy at the inlet. If you look at the diagram very carefully, we've been given the temperature and the pressure, and we are being told that it is steam. So we can go to the steam table, read at this pressure and at this temperature, the particular enthalpy. So that will give us H1. We can also go to the steam table and then read the saturation temperature at this point. So here we are told that the quality is 1. It means that it is a vapor, right? It is a pure vapor, or it is just a vapor. So we can read, or I mean, we can also tell us that we are dealing with something that would be saturated or could be saturated. So we'll read the saturation. I mean, at this pressure, we can read the enthalpy. So it's the enthalpy we are looking at. So we can now put that value in there for H2. And then we can find the difference between them, right? So we can put that in this expression. We already have the mass flow. Okay. Okay, but the mass flow wasn't given. So we have to find the mass flow as well. So to find the mass flow, we know that if I have density, it's equal to my mass over my volume, right? So 1 over density is volume over mass. That's my specific volume. So we also read those values from the steam table, right? But then, as we said, from this relation here, we can say that mass is equal to density times volume. And we said 1 over density is the same as specific volume. So let me just put subscript S here so that we differentiate them. So the density here, I can make it 1 over my specific volume times my volume that I am looking at, right? And then this volume here, I can represent it with, or this volumetric flow, because now I'm dealing with a flow rate. It's M with a dot on top. So it's now a flow. So this volumetric flow now, I can make it area times velocity. So one thing to notice is that volumetric flow is area times velocity. So this is what we are trying to say. Let me represent volumetric flow with Q. So we can have Q to be equal to our area times our velocity, right? The reason why we are saying this is that this is supposed to be volume over time. And we know that volume is area times distance or times length over time. And length over time is the same as velocity, right? So I can just say that my volume over time is equal to my area times my velocity. Now the question gave us the diameter, and we are assuming that we are working with something that is cylindrical. So if we want to find the area, is going to be pi d squared over 4, right? The cross-sectional area, pi d squared over 4. Is that okay? So that can be our area term. And then the question also gave us the velocity as 200 meters per second from the diagram. So we have the diameter, we have the velocity. So once we have the diameter and the velocity, we can find the area, multiply to the velocity, and then we can get that volumetric flow term. And as we were saying down here, the volumetric flow term, so this V here, I can now make it the Q. It's representing the volumetric flow. So the volumetric flow over the specific volume will give me the mass flow. Is that okay? Yes, the slides will be sent to you. The slides will be sent to you. So that'll give you the mass flow. So in order to find the mass flow, I'll first find my area. I'll find my velocity. And then I'll take my my specific volume, which I'll get from the steam table. When I put them into this expression, I'll get the mass flow. Okay, so I'll get the mass flow. So I can now put that mass flow into this expression here. My H2 and H1, I read them from the steam table. So I can put everything in there and then I'll get the work that is done in kilowatts. On the next part of the question says that we should show that the kinetic energy change is negligible. So for the kinetic energy change, you know that kinetic energy is going to be 1/2. Then we'll have a V2 squared minus a V1 squared. Is that okay? So one thing to note is that we now have to find V2, but then the mass flow is not going to change. So whatever mass flow I found previously, I can also relate it to the area and the velocity and the specific volume at the other side. So what we are just trying to say is that since the M is the same, then A1 V1 over V1 should equal to A2 V2 over V2, right? But then this expression here, we're saying is also equal to our mass flow. So from that, we can get this expression where we make the V2, the outlet velocity, the subject. Is that okay? And we can find the area as well. So if we're given the diameter of the outlet as well, so we can also find the area as well. Then we can put that in and then get the outlet velocity. So we just know that a change in our kinetic energy is going to be half times our mass flow. So I was supposed to bring mass flow here, times our mass flow times the V2 squared. That's the outlet minus the V1 squared. And when I do that, I'll get my answer in watts, right? And I can change it to kilowatts. So when I compare this to the work we saw previously, this is 6.2 kilowatts. But the amount of work we did when we neglected kinetic energy was 3548.6 kilowatts. So realize that this 6.2 is very small compared to this 3548.6. Right, so that's why we are seeing that kinetic energy will be negligible. Is that okay? And please really pay attention to units in this case, because realize that here the enthalpies were in kilojoule per kilogram. So at the end of the day, when we multiply it by the mass flow, which is in kilogram per second, we are having kilo. Writing is a bit hard. Okay, we are having we are having kilojoule per kilogram. We are multiplying it by kilogram per second. So now we end up with kilojoule per second. That's why we are getting kilowatts. But we are doing it for the kinetic energy. Realize that we are having kilogram per second, right? And then we are just multiplying it by this is the velocity. So the velocity is supposed to be in meters per second. And then we squared everything, right? If you should do this and check the dimensions, you are not going to end up with kilowatts. You're going to end up with watts. Is that okay? So please pay very close attention to the units. in this case, we already had kilojoule in the question. That's why our final answer was in kilowatts. But here, if you should simplify it further, you are going to get joule per second, not kilojoule. So please pay very close attention to the units. Okay. So I think our time is up. We would end it here today. Tomorrow we'll finish with the valves and then the heat exchangers and then the boilers, and then we'll be done. So I'll send the material to you. You can go through. If you have any questions, you can reach out to us on the page. And please try out all the examples in the slides. If you get stuck, you reach out to us and then we'll help you out with that. Okay, so I'll send the attendance link right now. And while I'm doing that, if there are any questions, please you can ask. Any questions? Someone is asking what the attendance to be used for. So the thing about the attendance is that it's not everybody who is going to join. And at the end of the day, if we are supposed to um, certify people based on the fact that they joined the class or they took part in the assignments, this is what we are going to use as a reference. So that's the attendance link. So let's do all to fill it. And then we'll continue tomorrow, God willing.